module, you will learn about the relation between Ka and Kb. You have learned that a weak acid is related to its conjugate base through the equilibrium constant expression Ka, and a base is related to its conjugate acid through the equilibrium constant expression Kb. As the conjugate acid-base pairs are related through the equilibrium constants, you can also assume that the equilibrium constants for an acid-base conjugate pair are also related to each other. Consider the dissociation of weak acid HA in water. The acid dissociation constant, Ka, for this equilibrium can be written as Ka is equal to the product of concentration of H3O plus and A minus ions divided by concentration of HA. HA, being a weak acid, has a strong conjugate base A minus. The dissociation equilibrium of strong conjugate base A minus in water can be represented as A minus aqueous plus H2O liquid in equilibrium with HA aqueous plus OH minus aqueous. The base dissociation constant, Kb, for the dissociation of this base can be written as the product of concentration of HA and OH minus ion divided by A minus. On adding these two reactions together, the common terms cancel out, leaving the autoionization of water. The equilibrium constant for the net reaction may be expressed as K net is equal to the product of concentrations of H3O plus and OH minus divided by concentration of water raised to the power of 2. As the concentration of water remains almost constant, it can be ignored. Hence, K net is equal to product of the concentrations of H3O plus and OH minus ions. Recall that the product of H3O plus and OH minus ions is equal to Kw, the ionic product of water. Thus, K net is equal to the product of concentrations of H3O plus and OH minus, which is equal to Kw, the ionic product of water. Note that the equilibrium constant for the new reaction is the product of the equilibrium constants of the individual reactions. That is, the product of Ka and Kb is equal to the product of concentration of H3O plus and A minus divided by concentration of HA multiplied by the product of concentration of HA and OH minus divided by A minus. On cancelling the common terms, you get the product of concentration of H3O plus and OH minus. This, as you know, is equal to Kw, the ionic product of water. Hence, it can be concluded that the product of Ka and Kb is equal to the ionic product of water. This leads us to conclude that the equilibrium constant for a net reaction obtained after adding two or more reactions is equal to the product of the equilibrium constants for individual reactions. On applying the logarithmic scale to the equation, we get pKa plus pKb is equal to pKw. which is equal to 14. Some of the acids can donate more than one proton in their aqueous solution. Such acids are known as polyprotic acids or polybasic acids. For example, sulfuric acid and oxalic acid, which have two ionizable protons per molecule of the acid that can be donated, are called dibasic acids. Phosphoric acid, on the other hand, is called a triprotic acid as it can donate 3 protons. Consider the ionization of a dibasic acid, sulfurous acid, in water. Its ionization can be represented in the form of an equation as H2SO3 aqueous in equilibrium with H3O plus aqueous and HSO3 minus aqueous. The first acid dissociation constant, represented by Ka1, is equal to the product of concentration of H3O plus and HSO3 minus divided by concentration of H2SO3. Experimentally, its value is found to be 1.7 multiplied by 10 to the power of minus 2. Similarly, the ionization reaction of HSO3 minus can be represented as HSO3 minus aqueous in equilibrium with H3O plus and SO3 minus 2 aqueous. The second dissociation constant, represented by Ka2, is equal to the product of concentration of H3O plus and SO3 minus 2 divided by concentration of HSO3 minus. The experimental value for this dissociation is equal to 6.4 multiplied by 10 to the power of minus 8. Did you observe that Ka2 is smaller than Ka1? For any polyprotic acid, the first proton is lost easily, while the last proton can be removed with great difficulty. It can be seen that the second proton has to be removed from a negatively charged species. Due to the electrostatic forces, it becomes difficult to remove a positively charged proton from the negative ion. Hence, for a polyprotic acid, the higher order ionization constants are smaller than the lower order ionization constants. Have you ever wondered why some acids are strong and some are weak? The extent of the dissociation of an acid or the strength of an acid depends on the strength and polarity of the HA bond. In general, the weaker the HA bond, the less is the energy required to break the bond and the stronger is the acid. With an increase in the electronegativity of the atom directly attached to hydrogen, the charge separation between the atoms increases. This results in a weakening of the HA bond and an increase in acidity. For instance, the order of acidity of HF, H2O, NH3 and CH4 is HF greater than H2O greater than NH3 greater than CH4. The HF bond, because of its greater polarity, has less bond dissociation energy. This qualifies it to be stronger than the other given molecules. However, note that HF is a weaker acid than HI. Let's see why. Remember that while comparing the elements in the same group, the acidic strength increases with an increase in the size of the atom directly attached to the hydrogen atom. As the size of A increases down the group, the HA bond strength decreases, and hence the strength of the acid increases. Thus, the acidic strength of halogen acids decreases from HI to HF in the same order in which the size of the halogen atom decreases. Consider the dissociation of acetic acid in water. The equilibrium for this dissociation may be represented as CH3COOH aqueous in equilibrium with H plus aqueous plus CH3COO minus aqueous. Suppose you add a strong electrolyte such as HCl, which furnishes H plus ions to this equilibrium. What do you expect? Following Le Chatelier's principle, this equilibrium will be shifted to the left, suppressing the ionization of acetic acid. Similarly, if you add sodium acetate CH3COONA that furnishes CH3COO minus ions, the equilibrium also shifts to the left, suppressing the ionization of acetic acid. These are both illustrations of the common ion effect. The common ion effect may be defined as the shift in the position of an ionic equilibrium caused by the addition of a solute that provides an ion that is a part of the equilibrium. You will learn how to evaluate the pH of the solution when an electrolyte containing a common ion is added to a weak acid or base through a problem. Calculate the pH of the solution resulting from the addition of 0.1 mole of sodium acetate to 0.1 mole acetic acid solution. Ka for acetic acid is equal to 1.8 multiplied by 10 to the power minus 5. The dissociation equilibrium of acetic acid in water may be represented as CH3COOH aqueous in equilibrium with CH3COO minus aqueous plus H3O plus aqueous. To determine the equilibrium concentrations of the substances, set up an ICE table. Let X be the extent of ionization of acetic acid. The initial concentrations of CH3COOH, CH3COO minus and H3O plus are 0.1, 0.1 and 0 moles respectively. The change in concentration after the dissociation of acetic acid is equal to minus Xm for acetic acid plus Xm for H3O plus ion and plus Xm for acetate ion. The equilibrium concentrations of CH3COOH, H3O plus ion and CH3COO minus ions are 0.1 minus X moles and 0.1 plus X moles respectively. The equilibrium constant expression for this reaction can be represented as Ka is equal to the product of CH3COO minus and H3O plus divided by concentration of CH3COOH. Substituting the value of Ka and of the equilibrium concentrations of acetate, hydronium ions and acetic acid. We get 1.8 multiplied by 10 to the power of minus 5 is equal to x multiplied by 0.1 plus x divided by 0.1 minus x. As the acid dissociation constant Ka is small for a weak acid, the extent of ionization x can be assumed to be very, very small than 0.1 mole. Hence, you can assume that 0.1 plus x is nearly equal to 0.1 minus x, which is nearly equal to 0.1. Thus, 1.8 multiplied by 10 to the power minus 5 is equal to x multiplied by 0.1 divided by 0.1. This is equal to x, which is nothing but H plus or H3O plus ion concentration. Thus, the pH of the solution is equal to negative log of 1.8 multiplied by 10 to the power of minus 5, which is equal to 4.74. You have now reached the end of this module. In this module, you learned that the equilibrium constant for a net reaction obtained after adding two or more reactions equals the product of the equilibrium constants for individual reactions. pKa plus pKb is equal to pKw, which is equal to 14. Acids that can donate more than one proton to a solution are known as polyprotic acids or polybasic acids. Sulfuric acid and oxalic acid, which have two ionizable protons per molecule that can be donated, are called dibasic acids. Phosphoric acid is called the triproptic acid, as it can donate 3 protons. The extent of dissociation of an acid depends on the strength and polarity of the HA bond. In general, the weaker the HA bond, the less is the energy required to break the bond and the stronger is the acid. In a group, acidic strength increases with an increase in the size of the atom directly attached to the hydrogen atom. The common ion effect may be defined as the shift in the position of an ionic equilibrium caused by the addition of a solute that provides an ion that is a part of the equilibrium.